This is one of my favorite demonstrations for applied force. I have what I call a wheel and an axle. My axle is this big drum in the center, and my wheels have rubber bands on the ends to give it some friction. What I'm going to do is I'm going to unroll my string on the axle and then roll it back again halfway. All right? And then I'm going to apply a force, okay, in the string. And I want you to predict which way you think the wheel axle will roll. Will it roll this way, or will it roll this way? Okay? Now my next question to you is this. Do you want to be right, or do you want to be wrong? How can that be? Because I can make it go this way. Or I can make it go that way. Or I can make it go this way. Or I can make it go that way. How can that be? How can that wheel go in either direction? Well, if you understand the nature of an applied force, you realize that there are two components to that applied force. One of the components is vertical, okay? And one of the components is horizontal. So what? Well, if you consider this angle theta here, as you lower the angle theta, the horizontal force will grow. If the horizontal force is greater than the force of friction, then it's going to go to the right. If you raise the angle theta, the horizontal force will decrease. If the horizontal force is less than the force of friction, then it's going to go to the left. So the equation that we're applying to this system is the sum of the forces, which include the applied force plus the opposing force plus the aiding force is equal to the net force. There's no aiding forces in this system. The applied force would be the horizontal component. The opposing force would be the force of friction. And if there's anything left over, that would accelerate the wheel in the direction where the force is maximum. If the horizontal force is greater than the force of friction, then it's going to the right. If it's less, it's going to go to the left. It's a really good example of component vectors in sum of the forces.